The next part of our story is one of the most intriguing in all of the history of science. It's built upon the shoulders of Michael Faraday, who was the son of a blacksmith, had no formal education, and yet became one of the giants of 19th century science because he did two things. He developed the electrochemical cell, which we've just analyzed, but more than that, he discovered electromagnetic induction. And while we'll talk about that at a later time, electromagnetic induction made possible an electric motor. So that meant that Faraday could take his voltaic cell, and we'll represent it here as an electrochemical cell, which we're now extremely well informed about. It creates the flow of electrons in an external circuit, and he fed that flow of electrons into an electric motor, and the electric motor rotated a shaft, and that shaft could raise a mass against the pull of gravity. And that was a profoundly important breakthrough because the chemical potential is simply the change in Gibbs free energy, and we've analyzed that already. The electrical potential is the voltage that can be measured directly across the two feeds from that electrochemical cell, and we have just discussed how we actually calculate that voltage directly. But then the gravitational potential could be converted directly into the amount of work done because the mechanical energy that's intrinsic to the raising of that mass against gravitational attraction is a number that can be very easily calculated. The mechanical energy gain is simply the mass times the acceleration of gravity times the change in height that mass undergoes. That means that we have a direct calculation of the work done. And what Michael Faraday discovered was that the work done was proportional to the voltage, but it was also proportional to the number of electrons that flowed through the circuit. His hypothesis was that the maximum amount of work that could be done from an electrochemical cell was simply related to the change in Gibbs free energy. Our old friend delta G was equal to the maximum work done by our electrochemical cell. And in fact, as we will see later, delta G is the maximum amount of work you can extract from any chemical reaction, except that Faraday was the genius who hooked up his electrochemical cell to his electric motor and then simply measured the amount of work done per unit time by raising that mass from that simple little pulley, and he connected all three types of energy. So let's look at this. Work is voltage times the total charge through the system. That's what he hypothesized, and that in fact was correct. But we also have to take this apart a little bit. The total charge that flows through that system is equal to the number of electrons times the charge on each electron. And we know that the charge on one electron is 1.6 times 10 to the minus 19 coulombs. The number of electrons per mole multiplied by the number of moles gives us the number of electrons that have flowed through that circuit. So if we take the number of electrons per mole and multiply it times the charge on each electron, that number comes out to be 9.65 times 10 to the 4 coulombs per mole. That gives us directly the relationship that delta G is equal to the number of moles times the charge per mole times the cell voltage. And we have to put a minus sign out in front because of the negative charge on the electron. But that capital F is the Faraday constant that stands in honor of Michael Faraday, who intuited not only how to build an electrochemical cell, but also how to build an electric motor. And when he connected them all together, he connected three different forms of energy: mechanical energy, chemical energy, and electrical energy into one unified idea.